Ukraine just deployed a drone. Russia can't jam. And it's rewriting everything we know about electronic warfare. February 5th, 2026. Russian electronic warfare operators are flooding the battlefield with jamming signals. GPS is blocked across hundreds of square kilometers. Radio frequencies are saturated with interference. Every Ukrainian drone they've faced for 2 years stops working in this electromagnetic hellstorm. Except one. A new Ukrainian FPV drone is diving toward a Russian tank position. The operators watch it on their screens, waiting for it to lose signal and crash like all the others. But it keeps coming. Straight, precise, unstoppable. The jamming that's supposed to blind it does absolutely nothing, because this drone isn't using radio signals at all. It's connected by a fiber-optic cable, a physical wire spooling out behind it as it flies. Russia's billion-dollar electronic warfare systems can't jam a wire. They can't intercept the video feed. They can't disrupt the control signals. The drone is completely invisible to their countermeasures. And Russia has no answer. Tonight, we're revealing Ukraine's fiber-optic drone that just made Russian jamming technology obsolete, how it works, and why this simple solution is defeating Russia's most sophisticated electronic warfare systems. The war in Ukraine has been defined by rapid technological adaptation. Both sides continuously develop new weapons and tactics in response to what the enemy deployed yesterday. Ukrainian forces have become masters of this adaptation, turning commercial technology into military capability faster than traditional defense industries could imagine. The fiber-optic drone represents the latest evolution in this cycle, a response to Russian electronic warfare that's elegant in its simplicity and devastating in its effectiveness. Russian electronic warfare capabilities are among the most sophisticated in the world. They've invested billions in systems designed to dominate the electromagnetic spectrum. Massive truck-mounted jamming stations can deny GPS and communications across entire regions. Smaller tactical jammers protect individual units and vehicles. The doctrine is comprehensive. If the enemy depends on radio signals, deny them those signals. Blind their sensors. Silence their communications. Make their precision weapons worthless. This approach worked devastatingly well early in the conflict. Ukrainian drones that depended on GPS for navigation and radio links for control fell from the sky in large numbers when they entered Russian jamming zones. Artillery shells guided by GPS missed their targets. Communications networks went silent. The electromagnetic environment became so hostile that operating anything electronic near Russian forces was extremely difficult. Ukrainian engineers responded with various countermeasures. They developed drones with inertial navigation that didn't depend on GPS. They created autonomous systems that could complete missions without constant radio contact. They used frequency-hopping radios that were harder to jam. Each solution worked for a while until Russian electronic warfare adapted. The cycle continued with neither side achieving permanent advantage. Then someone had a different idea. What if you didn't use radio signals at all? What if you connected the drone to its operator with a physical cable? Radio jamming can't affect a wire. It's immune to electronic warfare by its very nature. The concept was so simple that it seemed almost primitive compared to the sophisticated wireless systems everyone was using, but simple solutions often work best. The technology itself isn't new. Fiber optic cables have been used for decades in communications because they offer enormous bandwidth and immunity to electromagnetic interference. Light pulses traveling through glass fibers aren't affected by radio jamming or electrical noise. The military has used fiber-optic cables for secure communications in fixed installations, but putting this technology on a small, fast-moving drone required solving several engineering challenges. The first challenge was the cable itself. It needed to be lightweight enough that the drone could carry it while maintaining flight performance. It needed to be strong enough to not break during aggressive maneuvers, and it needed to unreel smoothly as the drone flew away from its operator without creating drag that would destabilize flight. Ukrainian engineers experimented with various fiber-optic cables, eventually settling on ultra-thin fibers with minimal cladding. The resulting cable weighs only a few grams per meter and can withstand the forces involved in high-speed flight. The spooling mechanism was equally critical. The cable is wound on a small spool mounted on the drone. As the drone flies, the spool rotates freely, allowing cable to unreel naturally. The mechanism uses low-friction bearings to minimize resistance. A simple brake prevents the spool from over-rotating and creating slack that could tangle. The entire spooling system weighs less than 50 grams and adds minimal bulk to the drone's profile. Range is limited by cable length. Most versions carry between 5 and 10 kilometers of fiber-optic cable. That's significantly less than radio-controlled drones, which can operate at ranges of 30 kilometers or more with the right equipment. But for the mission profiles Ukrainian forces typically employ, 5 to 10 kilometers is sufficient. Most targets are within a few kilometers of the launch position. The trade-off between range and immunity to jamming strongly favors the fiber-optic approach. The optical transceivers that convert electrical signals to light pulses and back are miniaturized commercial components. These chips are mass-produced for telecommunications applications and available for a few dollars each. On the drone, a transceiver converts the camera's video signal and control inputs into modulated light that travels down the fiber. At the operator's end, another transceiver converts the light back to electrical signals for display and control. The bandwidth available through even a single thin fiber is more than adequate for high-definition video and control signals with minimal latency. Latency, the delay between operator input and drone response, is essentially zero. Light travels through fiber at about two-thirds the speed of light in vacuum, meaning signals take only microseconds to traverse several kilometers of cable. This is actually lower latency than many radio systems, which introduce delays through encoding, transmission, and decoding. Operators report that fiber optic drones feel more responsive than their radio-controlled counterparts. The operational advantages are immediately obvious. In environments saturated with Russian jamming, where radio-controlled drones become unreliable or completely unusable, fiber optic drones operate normally. The jamming that's supposed to protect Russian forces does nothing against a physical cable. Russian electronic warfare operators can broadcast as much interference as they want. It doesn't matter. The fiber optic drone is completely immune. This immunity extends to signal interception as well. Radio transmissions can be intercepted and analyzed. Russian intelligence has captured Ukrainian drones and reverse-engineered their control protocols. With that information, they can potentially spoof control signals or inject false commands. Fiber optic cables don't radiate signals that can be intercepted. The only way to access the data flowing through the cable is to physically tap it, which is impossible when the cable is unreeling behind a fast-moving drone. The psychological impact on Russian forces has been significant. They've grown accustomed to electronic warfare providing protection against drone attacks. When jamming is active, they feel relatively safe because most Ukrainian drones lose control. The fiber optic drones shattered that sense of security. Suddenly, jamming doesn't protect them anymore. Drones attack successfully despite all their electronic warfare measures. The protection they relied on proves worthless. Russian troops on the receiving end of fiber optic drone attacks initially didn't understand what was happening. They confirmed their jamming systems were operating normally. They detected the electromagnetic interference that should be blinding Ukrainian drones. Yet the drones kept coming. Some Russian soldiers reported seeing thin lines trailing behind attacking drones, but didn't immediately realize these were physical cables. The concept was so unexpected that it took time for Russian intelligence to assess what they were facing. Once Russian commanders understood the threat, they faced difficult questions about how to counter it. The obvious approach is to cut the cable. If you sever the fiber optic connection, the drone loses contact with its operator. But cutting a thin cable behind a fast-moving drone is extremely difficult. Small arms fire is unlikely to hit something so small. Even if bullets pass near the cable, they probably miss. The cable is too small and moves too quickly to be an easy target. Some Russian units tried deploying barriers of thin wires or nets at elevated positions, hoping the drone's cable would snag and break. This proved impractical. The equipment required is bulky and difficult to position effectively, and Ukrainian operators adapted by flying routes that avoided areas where such barriers might be deployed. The tactic occasionally succeeded but wasn't reliable enough to be a general solution. Directed energy weapons like lasers might be able to burn through the fiber optic cable if they could track and illuminate it long enough. But lasers that can damage thin targets at significant ranges are expensive and uncommon. Most Russian units don't have access to such systems. And the targeting challenge is substantial. Tracking a thin cable behind a maneuvering drone and maintaining laser focus long enough to burn through it requires precision that current systems struggle to achieve. The most practical Russian response has been to target the operators rather than the drone. The fiber optic cable creates a physical line pointing directly back to the launch position. If Russian forces can quickly identify where the cable originates, they can target that location with artillery or drones of their own. This creates time pressure for Ukrainian operators. They need to complete their mission and relocate before Russian counter-battery fire arrives. Ukrainian tactics evolved to address this vulnerability. Operators launch from positions they can quickly abandon. The fiber optic cable spools out from the launch point, but the operator doesn't stay there. After launch, they move to a different location, taking their control equipment with them. The cable trails back to the abandoned launch point. Even if Russian forces target that location, they're hitting empty ground. The operator is safely distant, still controlling the drone via the fiber connection. Some units use relay positions. The fiber optic cable runs from the drone back to an unmanned relay point, where the signal is converted to radio or another fiber segment that runs to the operator's actual location. This adds complexity, but provides additional security. Russian forces targeting the cable's origin point hit the relay position, not the operator. The relay equipment is relatively inexpensive and can be abandoned without losing critical capability or personnel. The manufacturing of these fiber optic drones is distributed across numerous small workshops and volunteer organizations throughout Ukraine. Unlike sophisticated military systems requiring specialized facilities, fiber optic drones can be assembled with relatively basic tools and materials. The fiber optic cable is commercial telecommunications grade, ordered from suppliers worldwide. The optical transceivers are off the shelf components. The drones themselves are based on commercial racing drone designs that have been weaponized throughout the conflict. This distributed production makes the system resilient. There's no single factory to target, no centralized supply chain to disrupt. If one workshop is destroyed, dozens of others continue production. The decentralized nature of Ukrainian drone production has frustrated Russian attempts to suppress it through strikes on industrial facilities. You can't bomb workshops that are scattered across basements, garages, and small businesses throughout the country. Cost is another decisive advantage. A complete fiber optic drone system, including the drone, cable, transceivers, and control equipment, costs approximately $800 to $2,200 depending on specifications. This compares favorably to radio-controlled systems of similar capability and is vastly cheaper than the military equipment these drones destroy. When an $800 drone can disable a multi-million-dollar Russian tank or artillery piece, the economic exchange strongly favors Ukraine. The Russians have attempted to copy the technology. Intelligence services obtained examples of Ukrainian fiber-optic drones from crash sites and captured equipment. Russian engineers examined them and concluded there's nothing technically sophisticated that couldn't be replicated. But replication requires establishing production capacity, training operators, and integrating the systems into doctrine and tactics. Russia's centralized military procurement bureaucracy moves slower than Ukraine's improvised, decentralized production networks. By the time Russian forces began fielding their own fiber optic drones in limited numbers, Ukrainian forces had months of operational experience and had refined their tactics extensively. The Ukrainian advantage in this domain isn't just technological, it's doctrinal and experiential. They've learned how to employ these systems effectively through hundreds of missions. That knowledge is harder to steal than the hardware itself. International military observers have taken note of fiber optic drone development with great interest. Several NATO countries have requested briefings on Ukrainian systems and tactics. The US military, which has invested billions in sophisticated radio-controlled drones, is evaluating whether fiber optic variants should be added to their inventory for operations in contested electromagnetic environments. The simple, low-cost Ukrainian solution might prove more effective than expensive American alternatives in certain scenarios. The broader lesson from fiber optic drone development is that cutting-edge technology isn't always the answer. Sometimes, revisiting older approaches with modern materials and manufacturing creates solutions that outperform more sophisticated alternatives. Fiber optic communications are decades old. The innovation was adapting them to small, expendable drones in ways that solve real operational problems. This pattern repeats throughout military history. During World War II, some of the most effective weapons were simple and cheap, rather than sophisticated and expensive. The Sten submachine gun was crude but effective and produced by the millions. The T-34 tank wasn't the most advanced design, but combined good enough capability with production efficiency that made it decisively superior to technically superior but rare German tanks. Simple, producible, effective beats sophisticated, expensive, rare. The fiber optic drone exemplifies this principle in the context of modern warfare. It's not the most advanced drone technology. It has limited range. The cable creates physical constraints, but it solves the critical problem of operating in jammed environments, and it does so cheaply and reliably. That makes it more valuable than far more expensive systems that don't work when electronic warfare is active. Ukrainian innovation in this conflict has consistently followed this pattern. When faced with problems, Ukrainian engineers and soldiers develop practical solutions using available materials and technology. They don't wait for perfect systems. They field good enough solutions quickly and refine them based on operational experience. This agile, iterative approach has proven more effective than traditional military procurement that takes years to field new capabilities. The cultural and organizational factors enabling this innovation are as important as the technology itself. Ukrainian military culture has embraced bottom-up innovation. Soldiers in the field identify problems and work with engineers to develop solutions. Bureaucracy is minimal compared to traditional militaries. Good ideas move from concept to production in weeks rather than years. This organizational agility is a force multiplier that compensates for resource disadvantages. Russia, despite having larger defense budgets and more extensive military-industrial capacity, hasn't demonstrated similar organizational agility. Their military bureaucracy is hierarchical and resistant to rapid change. Innovation must flow through official channels that move slowly. Field improvisation is less encouraged. This cultural difference has consistently favored Ukraine throughout the conflict despite Russia's material advantages. The fiber-optic drone is one example among many of this innovation advantage. Ukrainian forces have developed sea drones that attack Russian naval vessels. They've created counter-battery systems using acoustic sensors and commercial tablets. They've weaponized commercial quadcopters in ways their manufacturers never imagined. Each innovation responds to specific operational needs with practical solutions that work now, not theoretical capabilities that might work eventually. This approach has limitations. It's reactive rather than proactive. It solves immediate problems but doesn't necessarily prepare for future challenges. The solutions are often specialized for current conditions and might not transfer to different conflicts. But in the context of the Ukraine conflict, where immediate survival and operational effectiveness matter more than long-term theoretical considerations, the approach has proven successful. The fiber-optic drone's effectiveness raises questions about the future of electronic warfare. If physical cables make drones immune to jamming, does that reduce the value of sophisticated electronic warfare systems? Not entirely. Electronic warfare remains effective against most radio-controlled systems. But it introduces a vulnerability. Expensive electronic warfare equipment can be rendered ineffective by cheap countermeasures. This forces adversaries to invest in multiple layers of defense rather than relying primarily on jamming. Russian forces are adapting their tactics to account for fiber-optic drones. They're increasing use of physical barriers and camouflage to hide from drones that can't be jammed. They're practicing rapid relocation after drone attacks to avoid follow-up strikes. They're deploying more short-range air defense specifically designed to engage small drones at close range where cable length limits fiber-optic systems' effectiveness. These adaptations impose costs. Physical barriers and camouflage reduce mobility. Rapid relocation disrupts operations and reduces effectiveness. Additional air defense requires resources that could be used elsewhere. The fiber-optic drone forces Russian forces to divert attention and resources to defending against a threat they previously could counter with electronic warfare alone. The environmental impact of fiber-optic drones is worth noting. Each mission leaves behind several kilometers of thin fiber-optic cable scattered across the battlefield. This creates debris that will persist for decades. The cables are too thin to pose significant hazard to vehicles or people, but they contribute to the environmental degradation that's inevitable in war zones. Post-conflict cleanup will need to address this among many other forms of contamination. Some environmental advocates have criticized military use of disposable systems that create persistent debris. The criticism is valid but somewhat beside the point. War itself is environmentally catastrophic. The incremental impact of fiber-optic cables pales in comparison to destroyed cities, contaminated soil, and devastated ecosystems that result from sustained military operations. Addressing these concerns means preventing wars, not perfecting the environmental footprint of weapons used within them. The economic model of fiber-optic drone production is interesting from industrial perspective. Ukrainian production is largely funded through combination of government procurement, international aid, and crowdfunding. Civilian volunteers contribute money to purchase drones for specific military units. This distributed funding model allows rapid scaling without requiring centralized budget allocations. When a unit needs more drones, they work with volunteer coordinators who raise funds and arrange production. This model wouldn't work in traditional military procurement systems where centralized control and accountability are required. But in Ukraine's wartime environment, it's proven remarkably effective. Units get equipment they need quickly. Donors see direct results from their contributions. The production network responds to demand without bureaucratic delays. It's a case study in alternative military procurement that defense analysts worldwide are studying. Potential applications of fiber-optic drones extend beyond anti-tank missions. The same technology could be used for reconnaissance, flying the drone to observe enemy positions and relay video back through the cable. Communications relay is another application, where the drone flies to elevated position and serves as line-of-sight relay point for radio communications that would otherwise be blocked by terrain or jamming. Mine clearing might use fiber-optic drones to safely trigger suspected mines or provide detailed reconnaissance of minefields. Urban warfare scenarios particularly favor fiber-optic drones. Cities create complex electromagnetic environments with buildings blocking line-of-sight radio signals. Fiber-optic cables are unaffected by urban clutter. A drone could fly through buildings and underground passages, trailing cable behind it, providing reconnaissance in areas where radio-controlled drones would lose signal. Military forces worldwide are considering these applications for future urban operations. The limitation of cable length has prompted research into ways to extend range. One approach uses booster stations that receive the optical signal, amplify it, and retransmit it through additional cable segments. This could theoretically extend range indefinitely, though each booster adds cost and complexity. Another approach uses hybrid systems where the drone starts on fiber optic cable for the first few kilometers in heavily jammed areas, then switches to radio control once beyond the jamming zone. Underwater applications are being explored. Fiber optic cables work perfectly well underwater, and small underwater drones could be controlled via fiber for mine detection, reconnaissance, or attack missions. The cable eliminates the severe limitations radio communications face underwater. Several navies are reportedly testing fiber optic underwater drones for harbor defense and mine countermeasures. The human factors in fiber optic drone operation are similar to radio-controlled systems. Operators use FPV goggles showing the drone's camera view. They control the drone with handheld controllers similar to video game controllers. The experience is nearly identical to flying radio-controlled drones, which makes transition easy for operators already trained on conventional systems. Most operators report they can't tell the difference between fiber optic and radio-controlled drones during flight, except that the fiber optic version never loses signal. Training programs have emerged to specifically teach fiber optic drone operation. While the flying skills are identical to other FPV drones, there are specific considerations around cable management and tactics for missions where the cable is a factor. Operators learn to account for the cable's weight affecting flight dynamics as it spools out. They learn to avoid obstacles that might snag the cable. They learn tactics for launching and recovering while maintaining security. The psychological satisfaction operators report from using unjammable systems is notable. They've experienced the frustration of flying drones that lose signal and crash when entering jammed areas. Switching to fiber optic drones that simply work regardless of electronic warfare is empowering. They can focus on the mission rather than worrying about whether their control link will fail. This confidence translates to better performance and higher mission success rates. Russian soldiers' accounts of facing fiber optic drones describe frustration and helplessness. They activate jamming, confident it will protect them, then watch drones attack successfully anyway. Some report questioning whether their electronic warfare equipment is even functioning, running diagnostics mid-battle to confirm it's transmitting. The equipment works perfectly. It's just useless against this threat. That realization is demoralizing. The propaganda value of fiber optic drones extends beyond their military effectiveness. Ukraine has effectively communicated the narrative of clever, innovative defenders defeating a technologically superior aggressor through ingenuity. Videos of fiber-optic drones successfully attacking Russian targets despite jamming reinforce this narrative. International audiences see Ukrainian resourcefulness overcoming Russian sophistication, which builds support and sympathy. Russia's propaganda response has been inconsistent. Some Russian media downplay the effectiveness of fiber-optic drones, claiming they're rare and operationally insignificant. Other sources acknowledge the threat, but emphasize Russian countermeasures, which may or may not actually be effective. The inconsistency suggests Russia hasn't settled on a coherent narrative to explain why their expensive electronic warfare systems are being defeated by cheap Ukrainian technology. The long-term implications of fiber-optic drone development extend beyond this specific conflict. The technology demonstrates that physical connections still have relevance in an increasingly wireless world. When wireless systems become too vulnerable to electronic attack, falling back to physical cables provides immunity that's difficult to defeat. This lesson applies across military and civilian domains. Critical communications might need cable backups when wireless networks are jammed or attacked. The development also highlights the importance of low-tech solutions to high-tech problems. Military planners often assume that countering sophisticated threats requires equally sophisticated responses. But sometimes simple answers work better. A fiber optic cable costing a few dollars defeats electronic warfare systems costing millions. That asymmetry is profound and challenges assumptions about military technology development. For Ukraine, the fiber optic drone represents another successful adaptation in a war defined by continuous innovation. They identified a critical vulnerability in Russian defenses, the reliance on electronic warfare to protect against drones, and developed a simple counter that Russian forces struggled to defeat. This pattern of identifying weaknesses and exploiting them has characterized Ukrainian operations throughout the conflict. For Russia, the fiber optic drone is another frustrating demonstration that expensive systems and sophisticated technology don't guarantee success against determined, creative opponents. They've invested heavily in electronic warfare, and it's being bypassed by improvised drones connected with commercial fiber optic cables. This forces them to rethink their approach and invest in additional countermeasures, further straining resources. The broader military community is taking notes. Every innovation in Ukraine is studied by military organizations worldwide, assessed for lessons applicable to their own operations. The fiber optic drone is being analyzed in military colleges. defense contractors are developing variants, and doctrine writers are considering how to integrate such systems into broader operational concepts. The future might see hybrid systems combining fiber optic immunity with other technologies. A drone might use fiber optic cable for the first few kilometers, then deploy a mesh network for extended range. Or it might carry multiple cable spools, dropping one when it runs out and switching to another, creating segmented cables that are harder for enemies to trace back to operators. Innovation breeds further innovation. For now, the fiber optic drone stands as testament to Ukrainian ingenuity and adaptation. It's invisible to Russian electronic warfare. It can't be jammed, spoofed, or intercepted. It's cheap to produce and easy to use, and it's giving Ukrainian forces capability to strike Russian targets even in the most electromagnetically hostile environments. Russia's sophisticated jamming systems, which were supposed to protect their forces, prove worthless against a simple cable. That's not just a tactical advantage. That's a strategic victory achieved through clever thinking and practical engineering. The invisible drone that Russia can't jam is rewriting electronic warfare doctrine, one fiber optic cable at a time.